I think that will be good for your review of our lecture. So let's say now it is started, and yes, seems that it's working hopefully. So when you need our recorded lectures, then please have a look at my YouTube channel. Okay, then let's come to our lecture note. Okay, so this is already lecture 12, and as you know, as I announced before, so we will have next Monday we will have the midterm examination. But if any of you get sick due to the COVID-19, so cannot attend this offline examination, then the examination itself will be cancelled. So there is no online participation for this examination. Okay, so of course you cannot just say that, oh, I'm sick, so please cancel all of them. So it's not possible. So if you are really get positive for COVID-19 test, then please send me the official letter to me, so then I can announce the cancellation of our midterm examination to all of you. Then instead of taking that examination, so the problems will be distributed to you as a form of homework problems. So anyhow there will be some evaluation, but point is offline examination, so no online participation is allowed. Okay, so are you all with me? And I hope that maybe we can help safely take the exam, because it is much more convenient for you. So if not, maybe you have to spend also homework and other examination, so that will take even longer than the usual paper examination. Okay, so do you have any question about the lecture contents up to now? So I think that from my own experience, usually students when time is getting close to the midterm examination or final examination, sometimes students get more involved with the lecture, and they gave me many questions, really good questions, because they start thinking, oh, how can I solve those problems? So then tons of questions which was just hidden can be found, and I like to take those questions. So if you have any question before starting our lecture today, then please let me know. So anybody, then also you are always welcome to interrupt me by your question. So if not, then I will move to our lecture 12. So lecture 12 will be devoted to some contents about how can we solve this non-linear system. Maybe you can realize that the first half of our lecture was almost entirely devoted to the journey to find out a non-linear element. So as a result of that journey, you have found that there exists a certain circuit element. So it has two terminals. So it has two terminals and one terminal which can be regarded as a reference, that is called as cathode. And there is other terminal where we believe that this is sometimes higher than cathode or lower than cathode, that is called anode. So voltage across between two terminals, anode and cathode, can be regarded as the applied voltage. An important point is, when we have applied voltage larger than 0, then it behaves like a good conductor, like just a resistive component. And if we have negative values, although the magnitude is the same, but it does not conduct at all. Of course, we have a really small amount of current conduction, but compared with the one for positive bias, forward bias, that is really negligible. That was our journey to find out this kind of circuit element. So the answer, how can we generate or fabricate such a kind of circuit element, was amazingly simple. The answer, one possible answer was, okay, p-n junction can act as a diode. Of course, there are different circuit components which can act as a diode. So the p-n junction is not the only possible way to realize diode. So of course there can be different ways, but in this course the representative one is a p-n junction, and just to change the polarity of your doping profile, then you can easily get such kind of non-linearity. So when you apply higher voltages to a region where p-type doped, then you will have a forward biased p-n junction, and if you apply higher voltage to n-type doped region, then you will have a reverse biased p-n junction. So any question? So we have spent already 11 lectures here. However, that can be summarized in that way. So now we have a nonlinear component at our hand. Okay, now compared with the previous one, for example, let's think about this case. Yes, now we have a resistor. Then let's call it as an input, and let's call the voltage of this node as output. Then how can you calculate the output voltage from your information about the input voltage? So it is amazingly simple. So let me just answer that question. So the node voltage of output node can be easily obtained by just linearly depending on the input voltage, and let's say that this is R1, okay, R1 and R2, then maybe you easily understand this is given by just the total sum of your two resistors. Then what will happen here? So there will be just R1. So if you apply certain voltage like 1 volt as an input voltage, then you will have just R1 divided by R1 plus R2. That will be your V out. And if you just increase the value of your input, doubled, 2 volt, and you will get 2 times this number. So that is quite easy and simple. Then my question is, okay, they are all linear component, and how about this? Instead of this R1 and R2, we can think about a different configuration like this. Yes, now we have a diode called, for example, D1 and R1. Then maybe it is not that straightforward to find out the answer of output voltage. So isn't it possible, for example, if you say so, for example, okay, instead of R2, I will use certain information about taken from R1. Yes, also here R1. Maybe you can try to find out this way. Maybe we can find a certain resistance related quantity. Yes, maybe. However, it will be really difficult to find out this D1 related quantity, because you know now our D1 is no longer a linear component, and its behavior cannot be expressed as a linear relationship between terminal voltage and terminal current. So that will be quite complicated. That is the main topic of our lecture today. Okay, do you have any question about today's lecture contents? No? Okay, so we will revisit this topic, so after about 20 or 30 minutes later. And before starting today's main lecture, I just prepared some graphs to help your understanding on the PN junction. So let's just spend 20 or 30 minutes on those graphs. So I have prepared. I hope that it will be interesting, at least some of you. Okay, then how can I magnify it? Okay, so now you can find, for example, these graphs. So what is this? This is typical graphs we can find in literature or in reality. So it is so-called IV curve, you know it. So y-axis is current of a certain circuit element, and what is it? X-axis is corresponding to voltage of certain circuit element. Of course, if you are working with a resistor, then how does it look like? It just pass. Oh, sorry about that. So this is not exactly 0, so here we have a negative sign. So this is origin. The resistor always passes through the origin, because when you apply 0 voltage, then you will have a 0 current. That's true. So that's true for all of these components. And let's just draw a certain line, straight line. Yes, then that will be the graphs for a resistor. If you have a resistor, any resistor will just show up like a straight line. And of course, the curve is given by I equal to V divided by R. So therefore, here we have a slope of this straight line, and its slope is exactly corresponding to the inverse of our resistance. So think about this one. If you have a large resistance, then the graphs will be almost close to just a horizontal line. And if you have really small resistance, then what will happen? Then you will have a curve which is almost close to a vertical line. So you can easily understand this behavior. If you increase resistance, then it moves in this way, and if you decrease your resistance, then it will move in this way. Yes, this is the behavior of a resistor. However, now you are looking at the curve of a diode. So how can I get this result? So this result was obtained by assuming some facts like okay, M plus is doped with 10 to the 20 per cubic centimeter. Maybe you are quite familiar with this number. And p-type reason, okay, in this case I just took 10 to the 17, just like our beloved example. And yes, also, you know, there appears some quantities like mobility or diffusivity. So inside this system, maybe you have heard about that, because I gave you some homework examples which contains mobility and diffusivity. But those quantities are all assumed to be a constant or constant. So this is this assumption. And when we solve this system, so realistic system but with somewhat idealized parameters, then you will get this red line. Okay, how does it look like? So clearly, when you apply reverse bias, there is no current conduction error. That's it. If you apply positive bias, then still, for example, 0.2 volt or 0.4 volt, although you have applied forward bias, but it is not sufficient to turn on our diode in the range of this range. So having like 10 or 20 ampere per unit area. So it is not sufficient to turn on our device. But if we are going to, for example, 0.7, yes, now you can see the onset of your current, and after really a small incremental additional voltage, then now your curve just looks like this. almost looks like a vertical line. So say that what is the resistance of this element called a diode? It is really difficult to say because in the case of a resistor, we can clearly define a slope because it is just a straight line. However, since when we draw these IV characteristics of a diode, then it will not look like a straight line. So it is very difficult for us to find out a single variable called a slope. Of course, you can try to find out some differential slope everywhere. For example, oh, here we have a very large slope, and for example, here we have a very moderate slope, and in this case, we have almost zero slope for our scale. Okay, so I already. So the point is, since the diode is a non-linear circuit element, its IV characteristic is no longer a straight line, so we cannot define clearly a single slope, and so no concept like a resistance globally valid. Of course, instead of that, at a certain point, this point or that point, at every point, we can well define differential slope which can represent the behavior of small amount of changes. Okay, so do you have any question? We have a few more slides here, so if you have any question, then please interrupt me. You're really welcome to ask questions. Okay, then let's move to my next plot. Okay, so I have drawn the same quantity, same data. However, in this case, voltage and current are all, both of them are written in a linear scale. So starting from minus 0.8, it increases up to 0.8, and the scale is linear. And also in y scale, so starting from 0 and here 40, so it just grow linearly. However, you know that the behavior of this curve actually follows the exponential rule. So maybe in order to find out real functional dependence, it is better to represent the y-axis not in a linear scale but in a logarithmic scale. So I will show you the IV characteristics, the same data but written in a semi-log scale. So that is called as semi-log scale because only one of them is logarithmic. So of course, if we have both axes are in a logarithmic scale, then we say that that is a log scale. So we will see the graphs like this. Please note that this data is exactly identical. So I just took one single data and just plotted. Of course, added some more graphs to guide your eyes. But anyway, this is the same data. How does it look like? So previously our maximum was 40. Okay, so where can you find 40 ampere per square centimeter? So you can find that, oh, this is somewhere here, and our eye in linear scale can detect, for example, 5 or 1, but this is also corresponding to just number here. So in your linear scale, actually we can see only around here. If we take the linear scale, then that is the point or the range of data we can have good resolution. So previous graphs in the linear scale now converted into this semi-logarithmic scale, and all of that beautiful information previously seen from our previous curve now just merged into this not very interesting red color plot. Okay, so yes, since we debug this part, emphasizing on only this linear scale, this part, So our input, our curve is no longer very impressive. However, instead of that, we get more wider view on entire range. Previously, for example, when you say what is current value at this bias point, for example, if we apply minus 2 volt to our diode, then what will happen? Nobody knows in this scale, but now you can easily understand, oh, in this scale, if we apply minus 0.2 volt, okay, the current will be around, yes, 10 to the minus 10 ampere per square centimeter. Of course, please note that in this reverse bias mode, when you apply reverse bias, your current should be positive or negative. Obviously, your current should be negative. Then how did I draw this curve? So logarithmic of a negative number is not allowed. However, now you can see that I just took the absolute value of current. So please regard this quantity as a negative value. Okay, for example, if I have this number, then this is not like 10 to the minus 10. No, that should be regarded as minus 10 to the minus 10. So I just took the absolute value and drew it. And as you can see that, okay, it is quite amazing that if we apply, for example, negative bias or reverse bias to our PN junction, then current would be just about minus 10 to the minus 10 ampere per square centimeter. So this number is corresponding to what? So the reverse saturation current I sub S. So of course I have to say something. I sub S is strictly a quantity corresponding to current. So that has the unit of ampere. However, you can see that here the number has certain additional factor like a per square centimeter. But since we are talking about just one-dimensional structure, our quantities are always normalized with its area. So please note that in order to have a real, for example, real ampere scale, then you have to multiply the area of your diode, and that can be easily considered when you just inspect your wafer. For example, if you have 1 micro long and 1 micro long a square, then what will happen? You just multiply 10 to the minus 8 square centimeter to this system, because 1 micro and 1 micro is corresponding to 10 to the minus 10. So are you with me? So if we have a diode, if the top view of a certain diode looks like this, 1 micro and 1 micro, and this is your, let's say that this is your top view for PN junction, then the area is corresponding to 1 micrometer by 1 micrometer, and 1 micrometer is corresponding to 10 to the minus 4 centimeter again. So eventually you will get 10 to the minus 8 square centimeter. So for this system, we can easily understand the IS for this 1 micrometer square diode. IS will be 7.9 times 10 to the minus 19 ampere. Okay, so are you with me? So if we have a scaled version like 10 and 10, then what will happen? Then we will have 10, 10, 10 to the minus 3, 3, 10 to the minus 6. So we will have 100 times larger value. So 10 to the minus 17 ampere will be the order of our reverse saturation current. Okay, so are you with me? So all of our discussion is assuming one-dimensional analysis of our PN junction. So therefore there is a hidden factor like the area of our diode, and area of your diode can be recognized from the area of your terminal. So you can just multiply, then you will get the real current. And you can find that, oh, the scale is really small. I mean that the magnitude of your IS is really small. Even when you have one, yes, 10 micrometer and 10 microscale one, but that is really small. So of course, in reality, in your actual device, the size is not like a micrometer scale, no. So it is like just 10 nanometer by 10 nanometer, or around this number would be the size of your diode. So when you think about this one, then you can easily understand the IS, reverse saturation current, will be extremely small for your single PN junction inside your transistor or your chip. But please note that there are tons of, really billions, several billions of diodes inside your system. So although that number is extremely small, but we have to multiply also extremely large number. So we don't know how it compares for our actual application. Okay, so any questions? No question. Okay, then another one I wanted to say is this curve is really corresponding to almost perfectly clean PN junction. In reality, IS value of our PN junction cannot be low like this. This one is really super clean, super pure transistor, or super clean PN junction. In reality, there are a lot of mechanisms to increase this IS value. So please do not regard this value as a representative value. This value should be regarded as a minimum value we can achieve. Of course, it is not achievable in our really fabricated fabricated devices. And yes, so I just covered discussion about our reverse bias condition, and maybe you can find that I have introduced the symbols here. What is it? So just for beautiful curves? No, this symbol is corresponding to what? Corresponding to the analytic expression we have learned in our previous lecture. So do you remember? It was just written as I equal to IS, and exponential of VT normalized one minus 1. And if we just use IS value taken from our exact curve, then take the value summer voltage like 25.85 millivolt, and just to use this applied bias, then that is corresponding to this symbol empty circle. Then it means that red curve is not an analytical one. In order to achieve this red color, I spent some seconds using my workstation. So I have installed a certain program into my workstation, and it do certain heavy computation. So inside it contains all kinds of information. But important thing is, okay, after calculating, wow, then the curve can be really well represented by this amazingly simple one. Why we achieve such kind of good agreement? How did it? Red color was the result of heavy computation. So we spent quite much of time and memory, electricity, whatever. And this is just drawn using an analytical expression. The reason why we were able to get such kind of good agreement was this description or analytic expression takes the most essential part of this device operation. That's the point. I think that important thing you have to keep in mind in this engineering course is sometimes we have to deal with different systems. Right now, we are talking about PN junction, and later we'll talk about a transistor. However, if you are not working in microelectronics, if you are working with a different discipline of engineering, then your system of your interest will be different. But point is, if you are an engineer, then please try to find out what is the essential one. So the real system contains a lot of contents which affect to the final result, and some of them are really important and some of them are not that much important. As an engineer, we first identify what is the most important one, and since that takes that component, so what is the importance one is, okay, diffusion current component can be expressed as an exponential function of the applied bias. Since that part is taken into account in this expression, that's the reason why we have almost a perfect agreement in our simulation, numerical calculation result, and analytic expression. So please keep in mind that is not only for our course, but in your entire career as an engineer, maybe that will be a good lesson to keep in mind. And finally, in this slide, I wanted to say that I just manually calculated the slopes like this. 60 millivolt per decade slope. I emphasize that that is the typical slope of IV characteristics. So I just draw it. So without using any sophisticated means, I just say that I just yes, here 0.2 and here 0.3. So this is 5 times of 60 millivolt. So it should increase by factor of 10 to the 5. So 5 decades should be changed. So just I say that 1, 2, 3, 4, 5, and pick a point, and just I draw this slope, and that is just parallel shifted. And how does it look like? As you can see, red color is really obtained from computer simulation, but you can see that that exactly follows 60 millivolt per decade. So in our ideal case, even we don't like this 60 millivolt per decade. How about this? If we can achieve something like this, then maybe we will be very happy with this kind of description. So even for example, up to 0.4 volt, there is no current conduction, and once we achieve 0.4 volt, then the curve just increase like a rocket. Then we will be very happy with this one. However, unfortunately, we have no means to make or realize, fabricate such a kind of element. So this is restriction due to the physical law, because this exponential dependency is all related with the physical law inside our semiconductor material. So it is difficult to overcome that barrier. Of course, I told you in last lecture there are many attempts to get the break of this rule, but that is not related with this PN diode or PN junction, but related with the transistors. But if you are related or interested with the transistors, then maybe you have heard about the ways to overcome this rule. Okay, so I think that is all for IV characteristics of a PN junction. So if you don't have any further question, then let's quickly show other graphs and come back to our ordinary lecture progress. Okay, do you have any question? No? Okay, then let's go to other graphs. So those graphs, I have prepared 3 additional graphs, and they are just made to help you to understand our PN junction more deeply. So this is the same PN junction, yes, and I have prepared 3 different bias cases. So one is corresponding to 0.0 volt applied. What is it? This is the equilibrium case. So there will be no current conduction. And now we can consider both of positive 0.7 volt apply or minus 0.7 volt apply. Okay, this is reverse bias and this is forward bias. So if this device or this element is really a linear one, then their behavior will not be very interesting. But please note that this is position. So here you can see that this is position, and position 0 is corresponding to the junction between our n plus region and p-type region. So here we have n plus region and here we have p-type region. Okay, then how does it look like? Yes, electric field. Now this is the reference, the equilibrium one, and if we increase the reverse bias, the magnitude of reverse bias is now increases, then what happens? Oh, as you expect, the electric field is get even more stronger. So from the viewpoint of your electrons originally located in this part, your electron feel even stronger resistance about overcoming that depletion layer, so your electron cannot overcome further. Okay? And in this part, on the other hand, if we go to forward bias 0.7 volt, then as you can see here, now you have a much weaker electric field. So what will happen? In this case, your electron can easily overcome this depletion layer and you will have a lot more electron conduction. Okay, that is corresponding to our yes, intuitive understanding. And let's go to the distribution of hole density. So why do we care about hole density? So since this system is n plus p, what happens? So for n plus region, there will be almost no depletion. Okay, then instead of that, our depletion will appear only almost entirely in our p-type region, because p-type region has roughly 10,000 times smaller density compared with the n-type region. So as you can see that this is the behavior of your hole density. Okay, so if you are not educated at all, for example, then maybe you will feel that like this. This is the correct answer for your hole density. Of course, we all know that this is wrong. Yes, why don't you? Okay, I like it. So this is the doping density of your p-type region. However, we all know that due to the depletion layer, so there will be certain physical extent where we can find almost no holes. For example, this red color is corresponding to the behavior or distribution of your holes inside your system. Okay? For example, for this reason, the hole density is extremely small. Hole density is also extremely small only when we are around, for example, here 75 nanometer, then we can find a really small observable value for our holes. After that, it increase and eventually reach to the value like 10 to the 17. Why do we have 10 to the 17? It is because it is the doping density of our p-type region. Point is, we have in the lecture or in our homework, we have thought about the depletion approximation. So say that up to this extent, and the holes are completely depleted and we cannot find any hole at all. After that, once after we go beyond this depletion layer, we have full of holes. So this line, this vertical line, is corresponding to the expected behavior following the depletion approximation. However, the real solution red colors looks a little different. So are you happy or not very happy? Of course, when you first have a look at this, make a comparison between this red colored line and this straight vertical line, then your first feeling would be, okay, depletion approximation really doesn't work quite well. So maybe it's not. So although there is certain transition layer, so this is not negligible error. So you can find several 10 nanometer long. However, anyway, this is corresponding to certain closeness to the values like this. So, although not perfect, because you have to understand depletion approximation is really an approximation. However, that is really a successful approximation to consider your whole distribution. And another one is, up to now, we have thought about equilibrium case. Red color is corresponding to the equilibrium case because applied voltage was 0. Then now let's go to the reverse bias. Reverse bias, what will happen? Now we have even stronger electric field and even wider depletion layer. So please have a look at this black line corresponding to a reverse bias. Then what will happen? Okay, previously holes were there, and now it is further pushed back into p-type region. So now we can say in plain English like a depletion layer or depletion thickness gets larger. So we have even wider depletion layer here, thicker. And if we go to, for example, forward bias instead, then what happens? Yes, we have a much narrower depletion layer, and it is easy to overcome. So as a result of all kinds of this information, my final slide about physical quantity inside our system is electron density. Okay, electron density actually varies from quite much, and I intentionally deleted the part corresponding to 10 to the 20. Okay, so in n-type region, of course, its value is corresponding to 10 to the 20 because that is corresponding to your n-type dopant. However, please have a look at the values in your p-type region. What happens? If you have a look at this red colored one, you can easily understand the values far from this junction line is corresponding to what? So can you read it? So how large is it? The red colors just approach to this number, and this number is corresponding to 10 to the 3 per cubic centimeter. So what is it? 10 to the 3 per cubic centimeter is the expected electron density inside this p-type region. So it is not that much surprising to have electron in this level because this is corresponding to the minority carrier density of our p-type region. But as you can see, this red curve rapidly decreasing from so instead of that, now it is quickly just to go to the 10 to the 3. So yes, there will be no excessive electrons. So we expect that, okay, electrons are there. The amount of electron is just expected in the equilibrium case. However, please have a look at these two cases. Minus 0.7, reverse one, and positive 0.7, forward one. What happens? In this reverse case, now we means that our electron feel even stronger electric field, and it is almost impossible for our electrons to overcome this barrier. So as you can see, okay, there is really sharp decrease in our electron density. So in a reverse bias case, we cannot find almost no electron. Okay, previously we had really a small number of electrons, but now we have even smaller number of electrons in our p-type resin. Okay, nothing, not very interesting. So no current conduction as usual. But point is, now if you are looking at the electron density at a positive or forward bias case, then you can find that although this is a minority carrier, electron is a minority carrier in the p-type resin, and its value is just almost close to 10 to the 15. So compared with this 10 to the 3, the value is almost 12 orders of magnitude higher than its equilibrium value. In order to achieve such kind of huge difference in the electron density distribution, what did you do? The thing you have done in this system is just to increase the potential by amount of what? By amount of just 0.7 volt. So by changing your voltage by 0.7 volt, you can achieve the change of your electron density 12 orders of magnitude. Oh, 12 orders of magnitude is 1 trillion difference in the number. So that is the beauty of electronics. So by applying really small voltage difference, you can get really sensitive response of your electrical property. That's the point of this electronics. Okay, so I think that that's all for my prepared graphs. So if you have any question related with those 5 graphs, then please let me know. And any question? Okay. Then now let's come back to our lecture 12. So now we understand, okay, this p-n junction is really a non-linear system. Then anyhow, our goal is to find out V out. How can we calculate V out? It is no longer possible for us to just apply simple rule taught in the middle school or high school. We have to really apply what? At the beginning of our semester, we have learned that the only thing we have to keep in mind in circuit analysis is the Kirchhoff's current law. That is the only rule we have to keep in mind. So let's just apply the KCL to this. This node. For this out node, let's just apply our KCL. Then KCL simply means that the current should be conserved in a node point of view. So the current sum of incoming current should be the same of sum of outgoing current. So let's think about this one. Here we have a resistor current, and also we can find a diode current. So let's say that this is the direction of predefined resistor current and diode current. Okay, is heading this downward. Let's assume. Then from the viewpoint of our node here, certainly diode current can be regarded as an incoming current. Okay. Also, from the viewpoint of our node, this resistor current can be regarded as what? An outgoing current. So we can now say from the KCL, Kirchhoff's current law, okay, the diode current should be identical to resistor current. Okay. So do you have any objection against this KCL? Then please let me know. Then after that, now it is time to apply the specific equation for each element. So in the right hand side, we have a resistor. Then how can we express the resistor current in terms of voltage difference? So it can be easily obtained by R1 divided by voltage difference. Then what is the voltage difference? What is the voltage difference across this red colored our R1? So its lower terminal is just grounded. Yes, so we have ground voltage. Of course, here we have not drawn it explicitly, but we can expect that there is a ground signal hidden here. And how about this node voltage? Yes, this node voltage is not known to us, so let's just write it down as V out. Okay, so are you all with me? So I just applied the Ohm's law, and from the configuration I can easily identify its lower terminal is grounded and its higher current, higher terminal is denoted as V out. So that's it. Then let's go to this left side. Now we have to introduce the resistor. Instead of the resistor, we have to consider a diode. Then if we take the nonlinear expression for our diode current, then how does it look like? There is a reverse saturation current and exponential of what? Here we have to apply the voltage difference across our diode. The anode voltage minus cathode voltage should be placed here. Then my question is, what is the anode voltage and what is the cathode voltage for this device? Anode voltage is corresponding to this voltage, the voltage at this point, and cathode voltage is corresponding to, of course, this node. So you can easily understand since this node is directly attached to our input voltage source, so we can say that anode voltage is just corresponding to input voltage. So are you all with me? Then its cathode voltage is directly connected to our out node, so we will have out. So let me just write down once again. So just collecting them all. Now the KCL applied to this simple diode resistor system will just look like this: IS times exponential V in minus V out divided by VT minus 1. That is equal to V out and R1. So as you can see, IS is a parameter. From the problem, you know it. And input voltage, usually you know the input voltage because you apply 1 volt or you apply 3 volt, 1.5 volt, so you know it. What you don't know is here V out. You have no idea how the output voltage will be. And exponential, you know exponential, and R1 is also known to you because you have built that circuit. So you just selected 1 kilo ohm or 2 kilo ohm or 500 ohm. So that is your choice, so you know it. So the only quantity you don't know is V out. So you can interpret or you can treat this equation as just one non-linear equation for what? For V out. So just to solve a non-linear equation for V out. That will be all for this circuit analysis. So are you with me? now we have a nonlinear components inside our circuit. So each nonlinear circuit element introduce a nonlinear IV relation. So that complicated our analysis. But anyway, if you have a powerful computer, and if you can solve this set of nonlinear equations, then you can actually solve any kind of complicated circuit behavior. So then maybe you think that, oh, then should I write down such kind of program code? No, fortunately, that was already developed about 60 years ago. Yes, so that is really easily available to you. So I think that maybe if you have attended the circuit analysis course in your previous semesters, then you have already used those programs. So, have you heard about SPICE? Okay, then let's just focus on the students who have attended the circuit analysis. Could you please, if you have attended the circuit analysis, have you heard about the program called SPICE? Okay, that is really very interesting. So how can you live without SPICE in circuit analysis? But anyway, so that is the program called SPICE, and this SPICE is originally it was a specific name for certain program, like a rental car. So you know there's a rental car service, but one company make a catchphrase like a rent a car with hyphens, and after that it was really good success in its commercial. So after that, even other companies service rental car service is called as a rental car. So there was a few competing programs at the time. However, this guy was really successful, and nowadays all kinds of similar programs are just called as SPICE. And this is a program which can analyze the circuit. If you have a certain circuit, then you specify its net list. And what is the net list? I think that you have seen it already before. For example, yes, if we visit our homework and go to our latest homework, and okay, if you have a look at this one, yes, now you can easily find out the description about your circuit. Yes, it describes all voltage source, all diode, and all resistor, and their connection is specified in this simple 3 lines. And this is called as a net list, the network of circuit elements. So the net list, the SPICE program just read this net list and automatically solve the answer. Okay, so now with the SPICE, you can just easy to get the information about its circuit property. Then if we just stop here, then maybe that will be a good news. And okay, great, so the semester is over, please use the SPICE. Of course, it cannot be answer or conclusion of our entire semester. Although we can use the SPICE, yes, if you have just knowledge about how can we use the SPICE, and even after learning the net list and simulating the circuit with SPICE several hundred times, but you have no idea about what is it. So what is it actually? This one is corresponding to the rectifier you have studied in our course. So that's the reason why, although in real engineering life, you always use, as a circuit designer, you always use the spice and other computational means to help you. However, they just assist you and not teach you. So you should be educated and you have to understand before using the spice code or any kind of computational means, you have to understand what is it. Okay? So that's the reason why, although we have the spice, we now try to solve this equation. Yes, let's try to solve this equation. The most general way is like this. The general way is, first say, of course, let's assume that V1 should be given. V1, let's say that V1 is just 1 volt, and let's just say that IS is, what is the IS value we have assumed in our homework? So maybe that was just 0.1 femtoampere. So let's just say that we know the numeric numbers for these quantities. Then the way we follow is most general way. I will just explain the most general way. Just guess a certain Vout. So clever guy will guess a good initial guess, and a little bit less clever guy will find out a value which is far from your final answer. For example, if you say Vout equal to 1 volt, okay, it's okay. If you start from minus 1 volt, maybe not. 1 megavolt or minus 1 megavolt. Of course, this such a kind approach is not that efficient. So, for example, yes, maybe 1 volt can be a good way, or other ones can be a good way. So anyway, please try to find out a reasonable value. So then how can we get this reasonable value? Who told you this is reasonable and this is not reasonable? Unfortunately, it is very difficult to teach you about the feeling about what is reasonable or not. So I think that still we are in the range of that position. So if you are a little bit more experienced, then you will find that okay, this is a really poor guess and this will be a good guess. So once we have a good guess, then please just assume that this one is a good number. Then please try to evaluate those left hand side and right hand side. Left hand side and right hand side. How can I calculate this left hand side and right hand side, although I have no idea about the real number? I don't have the solution itself, but anyway, I have a temporal number, although not exact, but B out. Let's say that that is just 0.3. Then what will happen? I just insert 0.3 here, and here we have 1 volt, so the difference will be just 0.7, and it will give anyhow certain current number. So there is no guarantee that this calculated value is corresponding to the right hand side. Of course, when you just give, for example, 0.3 volt here, then if R1 is 1 kilo ohm, just like our example or our homework problem, then what will happen? So we will have 0.3 milliampere. So I will be doing. I mean that, for example, let's assume that I'm now trying 0.3 volt. Then we will have 1 femtoampere multiplied by exponential minus 0.7 volt Vt minus 1. Of course, this minus 1 is not that much important because this exponential compound is so huge. So we will have something like this. So So that will be corresponding to just 0.3 milliamps. Then what will happen? Okay, so for specifically for this system, if you are working with this specific type of problem, then you can make a really good approximation, because this -1 is not that important. Okay, safely removed, and you will have an approximate relations like this: VT 0.7 volt, and yes. Okay, then please compare them. Yes, this guy and this guy. Is there any guarantee that you have the equality? If you are quite lucky, then at the first shot you will get the answer. But of course, you're not in many cases. Then please compare them. Okay, for example, this guy is larger or that guy is larger. Then please try to update your temporal solution 0.3. Okay, 0.3 was not that successful. Then should I increase it or decrease it? Please check it. How can you do that? One possible way is just to, instead of 0.3 and 0.3, for example, you can try both of 0.331 or 0.29 volt. Then just to evaluate once again left hand side and right hand side, also left hand side and right hand side. The difference or the magnitude of this difference will determine or indicate the amount of error. If this number becomes small, then you are maybe approaching to the solution. If this error is getting larger, then maybe you feel that, oh, something is wrong, and maybe I'm not in the right direction. So then now you can just set the right direction. Okay, in this case, now I have to increase voltage a little further. Then please try another number, 32. Okay, if this one gets better, then just to increase repeatedly. Then maybe up to a certain point your error will get reduced. However, if you go beyond a certain number, like 0.4, 0.5, then you realize that, oh, now I have an even worse error, even larger error. So then what happened? Oh, just I test the solution point, then please turn around and come back. Then by following this way, so it's like this. There is somewhere, but we have no idea about what is the solution. What we can do is just to say that, oh, you have certain difference. So starting from here, let's measure the difference. Oh, you are far from. Okay, I will move this way. Oh, how about this? Your error is reduced. Okay, then let's go. Your error is further reduced. Okay, let's go. Your error is now further reduced. Good. Let's go. Your error is now increased. Oh, there is something wrong. So this part is the most close to your solution. Then instead of coming back to this way, be more conservative and take the small difference. Okay, this one. Oh, your error is getting smaller. By taking a repeated iteration to get the error and try to minimize it, then eventually you will find a certain numeric number. I'm not saying that on analytical solution, but you will get on analytic a numeric number which minimize or which reduce your error considerably. So in an engineering sense, then we can be satisfied with this number. Okay, so there is this small number, 10 to the minus 15, but I'm not care about that ampere difference. So I will be very happy with this one. That is the typical way we follow for analysis any kind of nonlinear behavior, nonlinear circuit. Of course, we have much more, how can I say, sophisticated and systematic way. Not just taking this amount of difference. So this is, of course, for educational purpose, how much we have to increase or decrease for next step. That is well determined by own method. So I just cite its name, so you can just have a about Newton method. Is this that Newton, the scientist Newton? Yes. So this is a famous guy who found out the law of mechanics, and this is called the Newton method. And if we apply that method to not a single variable problem, but if we have a set of coupled equation, usually we have a set of coupled equation because our system, our circuit contains a lot more circuit elements, so we have so many unknown variables. In this case, it's expanded form to multiple variable is typically called as Newton-Raphson method. So let me just wrap up today's lecture. So today's lecture was devoted to how can we generally analyze the circuit system. So circuit system can have multiple non-linear components, and the law, the only law we have to care about is just to apply KCL. Node-wise KCL, that's all. Then as a result of that analysis, we will have a set of non-linear equations, and that is really difficult to analyze by hand calculator or from our inspection. So the most general way up to now available to us is just to adopt a computational way to solve that set of nonlinear equations. However, as a circuit designer, if that is the end of story, then you can just draw circuit and try, say whether that is working or not, and just change slightly. Also run. That is not a life of a circuit designer. This is just to operator, just a learning program. So before starting any kind of calculation, you have to design your circuit. So in order to design certain circuit, you have to understand clear view on your circuit. What is it? What is the rectifier? What is this amplifier? What is this inverter or circuit, logic circuit? So that will be the topic of our remaining semester. Okay, so time is up, and this Wednesday we'll try to explain how can we simplify our analysis. Although not exact, but we'll try to find out an exact solution, an approximate solution for this system. Okay.